Hello student, today we will discuss some discontinuous function at the origin. Here I have taken three examples of discontinuous function. Now today we will learn how we can check discontinuity of function of two variables. So the first example is fxy is equal to 1 upon x square plus y square when xy is not equal to 0 and its value is equal to 0 when xy is equal to 0. So this is our first example. Now I just want to recall you that a function is said to be continuous at a point a comma b, then the simultaneous limit of function, that is limit xy tends to a comma b of x comma y, it should exist. Exist means its limit should be equal along different path. For different path, the limits should be equal. Number second, suppose if limit exists, then it will be equal to some value, say it is L. If L is equal to the value of function, when these two conditions are satisfied, then we say the function fxy is continuous at the origin, at point a comma b, at point a comma. If any one of these conditions are not satisfied, and then we say the function is discontinuous, otherwise discontinuous. So let us take first example first. In example first, we know that the value of function at 0 0 is equal to 0. Now we will find its simultaneous limit. So first of all, we take path along x-axis. And we know that along x-axis y is equal to 0. So the function fxy x square plus y square along x-axis, put in place of y is equal to 0, 1 upon x square. Now we will take limit x tends to 0 in f of x comma 0, and it gives us the value infinity. Similarly, if we take path path along y-axis. That is when x is equal to 0. Then also we get limit y tends to 0 f 0 comma x 0 comma y is equal to infinity. Now we will take a general path. Take a general path y is equal to mx, and we will find the limit of function at point 0 0 along the path y is equal to mx. So along the path y is equal to mx, fxy limit xy tends to 0 0 tends to 0 0, it will be equal to limit, in place of y we will use mx, so it become x tends to 0 f x comma mx, and this will be equal to limit x tends to 0 f 1 plus x square plus m square x square, and taking limit x tends to 0 it becomes infinity. So we can see from here that the simultaneous limit of fxy is equal to infinity, say this is equal to f, but it is not equal to the value of function, that is f00, which is 0. Hence the function fxy is discontinuous at the origin. Similarly, we can check the discontinuity of the second example. In second example, here the function is x to the power 4 minus y to the power 4 x to the power 4 plus y to the power 4 when xy is not equal to 0. Otherwise its value is 0. So here directly if we take y is equal to mx in this example, then limit xy tends to 0 0 f of xy is equal to, this will be equal to limit x tends to 0, and in place of y we will put mx. So here in place of y we will put mx, so it become x to the power 4 minus mx to the power 4 upon x to the power 4 plus mx to the power 4. Now taking x to the power 4 common from numerator and denominator, we get x tends to 0 1 minus m to the power 4 and 1 plus m to the power 4, and this limit depends on the value of small m. For different m we get the different limit of function, that means along different path. If we take m is equal to 1, that is y is equal to along x, y is equal to x path, its limit will be 0, and along y is equal to 2x path its limit will be different. So the limit, simultaneous limit of fxy does not exist at 0 0. Similarly, for the third example, where fxy is equal to x square plus y square upon x to the power 4 y square, we can